Hello everyone, today we're going to take a look at some past paper questions from IB. These are going to be trig modeling problems, so taking a sine or a cosine graph and adapting it to model like the movement of a Ferris wheel or something like that. These are IB HL questions, but they're also kind of a level that would appear on IB standard level. So I think this is going to be helpful regardless of which course you're taking, and we can just take a look at this first problem. So it says the following diagram shows a curve y equals a sine brackets k x minus d plus c, where a, k, d, and c are all positive constants. The curve has a minimum point at 1, 1 and a maximum point at 3, 7. And then we're asked to write down the value of a and the value of k. So whenever I'm doing a problem like this, I think it is helpful to have a sketch of what just a standard sine graph looks like, since basically what the problem is doing is transforming a regular sine graph to make it look like this with these 4 transformations. So if we know where we're starting, that's going to be a bit helpful. So a regular sine graph is going to look like this. It's going to come through, and I'm just going to do one kind of loop. This is one cycle, so it's going to have a period of 2 pi. As a default, all of these problems are going to use radians unless they tell you otherwise. So we're going to assume this is 2 pi. This, therefore, would be pi. And then we're going to have a minimum point here at halfway between pi and 2 pi. So 3 pi over 2, comma, minus 1. And up here is going to be just pi over 2, or 90 degrees, comma 1. So this is just going to help us get a sense of what changes we need to make to this graph in order to get the graph that's being described down here. All right, so for the first part, we're looking for the value of a and the value of c. So a and c on our function are the 2 y transformations. And we know they're y transformations because they're happening outside of the sine component of the function itself. So a times sine, that's going to be a scale factor. It's going to control basically how far apart vertically these components are, because it's going to stretch or compress vertically the graph. And then the plus c, that's going to be a vertical shift. So that's going to account for, in a sine graph, it's normally accounting for the midline, right? So this is the point that runs horizontally through our graph. You can't see that super well, but it runs horizontally here. On a regular old y equals sine graph, this is the x-axis, but on our transformed graphs, normally we've moved up. And this is the easiest number to find because it's just going to be halfway between our maximum and our minimum points. So our maximum point on the graph they're giving us is 7, and our minimum point is 1. So if we try and figure out what's halfway between them, we can go 7 plus 1 over 2 gives us 8. Gives us 8 over 2, which is 4. So our midline here is going to be 4, and that means C is 4 because our graph has been shifted up by 4. The other value, which is also not too difficult to find, is just going to be controlling how scaled up we are. And if we look at how that scale has changed vertically, we can see that the distance between our midline and our maximum point is 3, whereas over here that distance is just 1. So how much have we increased by? Well, we've multiplied by a value of 3, which means a is going to be 3. So those first 2 components are relatively straightforward to find, and that's part of the reason why the question is asking us to find these values first. The next thing we need to find is a value of k. Now k is an x transformation. We can tell that because it's within the brackets of our sine function. So it's affecting the x value before you apply the sine in like an order of operations sense. What that means is for all of our x transformations, they tend to do the opposite of what we're expecting. It's going to affect the x values, but here we have k times x. That's going to be, in reality, we're going to be dividing the values of x on our graph by k. It's always the opposite with x. What that means is we need to look at how much has this scaled up horizontally, right? This is not our horizontal shift. It's going to basically control the distance between the maximum and the minimum point, or the size of the period of our graph is another way of looking at it. So if we think in terms of the period, normally sine has a period of 2 pi, meaning you complete a full cycle every 2 pi angles, and then you would get another cycle for 2 pi and another cycle for 2 pi. We're going to be applying a k transformation to this, so we'll be dividing by k, because in our function it's multiplied by k, and then we will get the function, or the period of our new function. So how do we figure that out? Well, we have kind of our minimum and our maximum points here. We can see those x values. We can see that the distance between the minimum and the maximum horizontally is 1.5. But that's not a full period because we're not returning to our minimum point. A full period would be kind of double this, another 1.5. Our full period on our new function is 3. So how do we solve this? Well, we just rearrange it. So k is going to be 2 pi over 3. And that's our solution for the second part. Another way to approach this is to say, let's look at just the portion that we can see. So the portion that we can see is between our minimum and our maximum. So we know that that's going to be 1.5. On our graph, the distance between our minimum and our maximum point is, we can see pi. So then you would do pi over k equals 1.5. I'll try and draw a slightly prettier k. But if we rearrange this, we're going to get pi over 1.5 equals k. And then if you double the top and the bottom, you find that this is also 2 pi over 3. So either way, we're getting the same value of k as a solution. So now that we've done these first two parts, you can take a look at our final part, right? So this says find the smallest possible value of d, assuming that d is greater than 0. And this assuming that d is greater than 0, that part's going to be really important here, I imagine. Generally, when we get to the last part, these problems are always going to ask us about the horizontal shift last, or at least they tend to. There's a reason for this, and this is like the hardest part of the function to figure out. So they tend to leave this to last because it means that we can just plug a point into our equation instead of trying to figure out exactly how much we've shifted to the right, which gets a little bit complicated because technically there are many ways that you can shift to the right to get to this position because the function just keeps cycling forever. So if you imagine, we're starting out with something that looks like this. Well, if we want to move it so that we are crossing at our maximum instead of crossing at our beginning, because we can see here we're crossing at a maximum, how could we do that? Well, we could shift it to the left by a little bit. We could shift it to the left by a little bit more and we get the same result. And the same thing happens in the opposite direction, right? So we could, I've not really drawn the rest of it, but you could keep going further forward by one, by another set, and you would keep getting multiple values that look like this. So really the horizontal shift, it could be a number of different values. The easiest way to solve this then is just to plug stuff in to our equation. So what do we know so far? We know a is 3, so it's going to be 3 sine, we've got 2 pi over 3 x minus d, and then we've got plus 4. And this should be equivalent to 7 when we have an x value of 3. That would be one way of solving it. It's just plug the numbers in. So if we do that, we're going, okay, 7 equals 3 sine of, and I'm just going to multiply this out basically to make it a bit cleaner. But if we make x 3, we're going to wind up with 2 pi minus 2 pi over 3d. Here, 2 pi over 3d. And then the last part will have plus 4. And we're just going to rearrange this and simplify it a bit. So if I take 4 away from both sides, we're going to get 3 equals 3, and then the rest of it. If I then divide by 3, I'm going to get 1 equals sine 2 pi minus 2 pi over 3d. Okay, brilliant. I want to get to this point. I want to get to a point where it's clear to me what the value of the sine part of my function is going to be. Because often this goes along with a really common angle. And this is an example where that's the case. So we've got 1 equals sine of this whole function. I know what angle I need to put in order to get 1. I know pi over 2 or 90 degrees will work because of my function possibly because I have it memorized, but certainly because I've sketched it, I know that this is true. So, how do we solve this? Well, just some simple arithmetic, really. If I subtract by 2 pi, I can do the whole fraction subtraction thing, but this is going to end up being minus 3 pi over 2 equals minus 2 pi over 3d, just like that. Yes, that matches up. And then if you multiply it out, we're going to have basically minus 3 pi over 2 times minus 3 over 2 pi, and that gives us d. So this is just basically dividing by this value. With fractions, we flip it, so that's how I'm organizing this. We end up with 9 pi over 4 pi equals d, or you can cancel it, and this will give you 9 over 4 as our simplified value. So if we come back around, right, we're going to have a full function, h equals 3 sine 2 pi over 3 x minus 9 quarters plus 4. And that's our function. Now, one thing to note here, it did work with pi over 2, so that's brilliant. But there's always a possibility that this is not meant to be pi over 2, because there are other angles that will make sine equal to 1. So other examples of that, it's going to repeat on a 2 pi cycle, right? So we could have had pi over 2, as we did, or you add 2 pi to this, this gives you 5 pi over 2 would be another solution. You could go again, right? So what I'm doing here is I'm just adding 4 on the top, since 4 pi over 2 would be 2 pi. So this is 9 pi over 2, and then you could go like 13 pi. You're not going to need all of these, but there's a possibility you might have to test out the next solution in order to get the correct answer here. Hopefully that was helpful. There will be other videos covering this topic, so just pause as that drives past. There'll be other videos covering this topic, so there'll be a playlist I'm going to make, I think, through this week, so if you want to look at those are also going to be, I imagine, helpful.